today we will start the what in my syllabus what I call chapter 15 on capacitors and capacitance. So as an opening question, while I write this out, in the chat, does anyone know what a capacitor is? If you might have read it before or just know it from your daily experience, you know what a capacitor is. In one sentence, can you explain that? See if people have some idea. And the reference chapter for this in Giancoli, your textbook, is 24, 1 to 4. And 5, we won't go through that in depth. I'll mention what that is, but we won't really examine that. So I'll put that in brackets there. So anything, if I put in brackets in one of these references when I go through in lecture, what that means is we won't really examine heavily on that probably at all. Technically, it is part of the chapters we should cover in a normal session, but yeah, I'll relegate that to hopefully after you learn the basics, from 1 to 4, you will be able to use these transferable skills to learn things on your own, which is basically what I hope for you guys to be able to do. Okay. Anyone know what a capacitor is? Any guesses? It's no right or wrongs. So when you learn something new, the first thing you want to ask yourself is, what is it, right? What is it? How do you measure it? And why do we care about it? So we're going to answer some of these questions. The best way to answer what is it is think about, can you explain this concept to someone, to an 8-year-old or to a 5-year-old even? Can you explain this in simple language? That may not be the technical definition, but that shows if you can understand it well enough. Okay, if you cannot explain something in simple terms to a kid, you probably don't understand well enough what it is. I got a private message saying it's something that stored electrical energy. That is very good, yeah. And in even simpler terms, what I can do, that is actually very correct in terms of technical terms, is it's basically the world's simplest power banks. Okay, it's, probably a 5-year-old nowadays will know what a power bank is in our society. So it's a rechargeable battery. So I can actually call this, make a subtitle called this chapter is the theory of rechargeable batteries. So in the next 10 minutes, you will know how do rechargeable batteries work. And you'll be surprised by how simple they are. Just like, it's actually a little bit more realistic than what I explained as the physicist's definition of a battery. Remember, what is a battery? A battery is something that creates a potential difference, according to a physicist. That's all we care. It's a device that sets up a potential difference. Okay, you should have that definition somewhere written in your notes. If not, make sure you do. All right, so all right, how do we create a rechargeable battery? It sounds, but the first time you heard of this, if you have let's see if I have my power bank here. No, not here. All right. So if you have a little power bank, a little portable rechargeable battery, it might seem very intimidating what's going on in there, but you'll be amazed to see that it's actually very simple in principle. Okay, the principle is very simple. So how do we create one? All you need is 2 metal plates, put them next to each other, and you're done. Believe it or not. Okay, like that. Okay, so how do you charge it? Well, you first have to plug it in and to another battery, to a real battery, to charge up your rechargeable battery. So let's plug this in to a proper battery like this. So this is just 2 metal plates. What's going to happen? Well, one side is positive, one side's negative, right? The battery. Let's say this is a typical 9-volt battery you get from Walmart, and which means the potential difference, it sets up this 9 volts, which means one end has, let's say, the absolute value, absolute potential of 9 volts, and the other is 0, right? So the difference is 9. Again, let me reiterate, it doesn't matter what you call the absolute, it matters only the difference that affects what's going to happen. All right, so with a wire, remember what we learned about conductors in yesterday's lecture. So conductors means charges are completely free to move. So there's a million positive and negative charges, right? So all the positive charges would want to go from the high potential to the low potential. So we told you that they cannot go through the battery, as you see in the symbol. That's why this is a good symbol. It represents the fact that they couldn't go backwards. The real physics, what's really going on, or the real chemistry, what's going on, it's more complicated. It's inside. There's a chemical reaction that is pushing the positive charges to one way. So basically, it can't go the other way. But don't worry, if you take a chemistry course, you can learn all about that. We'll focus on the easy part, the outside, right? So they try to go from the positive, high potential to low potential, right? So this looks like a promising path. So they'll start to go. Remember also, if this is an ideal conductor, ideal wire with 0 resistance, then the potential here and the potential here, when I say potential, I don't mean difference, I mean absolute potential, is the same, right? So this is also 0 volts. So according to this guy, this positive charge, this looks very attractive. Pun intended there, it looks very appealing and it would like to go to a lower potential. So move all the way to here and it'll keep moving. And now it gets stuck because it cannot go any further if you separate it by some distance, right? Some gap, air gap over there. And all the positive charges will start going there and it starts to build up on the plate. Oops. Like that. At the same time, on the other side, right, the negative charges here will get repelled by this negative end, and we'll try to go as far away as the negative terminal as possible. If you'd like to think of the positive charge will get attracted to here, or you can think of equivalently, the negative charges will get attracted here. Either way you want to think about it, you'll get a lot of negative charges that gets pushed onto this plate, a lot of positive charges get pushed onto this plate. And now you've stored a lot of charges on this side, a lot of charges on this side. All right, so how much charge, let's say you have stored plus Q amount of charge on this side. How much charge do you think you can attract over here? From the symmetry of the problem, you would guess that there must be negative Q, right? Because if this is positive Q, it couldn't really attract more than any negative Q on this side, vice versa. So if everything is in equilibrium, let's say you have 100 coulombs over here and you only have 99 negative charges over here, 99 minus 99 coulombs of negative charges over here, then you have a net charge of +1, right? So it will still be able to it will attract probably an extra minus charge over here to balance it out, right? So if there's any imbalance, when in the charging period, you know, there might be a little bit of imbalance, but after a while, when it's settled down, then you should have a very symmetric situation with positive and negative. Okay. All right, so what do you do now? All you have to do is disengage the battery, disconnect the battery, right? So you disconnect, and then now you reconnect it to whatever your favorite appliance is. Maybe a light bulb, or your iPod, or your iPhone, whatever you want to charge. Let's assume they're all generically a light bulb, right? So now you have all these positive charges that were trying to go to the negative side, but failed because there's an air gap. Suddenly now has an outlet. They realized, oh, I can actually go this way now. Initially, the battery was setting up a potential difference, which was trying to prevent it to do that, right? It's the battery, that's the sole job of the battery, was trying to push the positive charge as far away as its positive terminal as possible, and the negative charge as far away as from its negative terminal as possible. So they all congregated and aggregated here. Now there's an outlet. You just connected it to a wire. Granted, this guy might have some resistance, right, in order to produce a light or whatever it's trying to power. But at least it's a way to go. So instead of jumping through the gap, which is impossible, it's actually not impossible if it's very high voltage across it. It might be, but let's assume this is a pretty good insulating piece of air, right? So they couldn't jump across. The best chance it has to go to the other side, right? This is negative, so it's trying to attract the positive is through the wire. And as they go through the wire, right, the flow of positive charge is exactly what we call a current. The current will go through here, which will light up the light bulb. And after a while, your end result is now they probably get neutralized. Positive, negative, positive, negative, positive, negative, right? Until your power bank runs out of, that's when it stops. You have to recharge it again. Okay, so the cycle goes back over here. So now you have been able to power the light bulb, right? So that's it. Other than a bunch of other technical formulas how to solve problems with this, we're done with the theory. This is how what I call the world's simplest power bank, 2 pieces of metal. Simplest power bank. All right, you can actually make one in your kitchen right away. Just take 2 pieces of metal, connect it to a battery, put them across with some distance. So the next slide, we're going to learn about how do I make a good one. Now, it's not just making one. We want to make a good chargeable battery, right? Lithium-ion battery. That sounds like a lot of chemistry words that I don't understand. If I understand it correctly, there's a private message there. If I understand correctly, lithium-ion batteries are not necessary. They might be actually rechargeable ones. I'm actually not sure. You can do a quick Google and see. But yeah, this is the basic theory of it, at least. There is slight subtlety. Yeah, the next slide I will tell you how do you make a good one, or how do you maximize the amount of battery you can charge, right, on it. It's not just good enough to make one, you want to make a good one. And also there is a small caveat is which is something actually a little bit beyond our syllabus, is if you use this very simple version, then the charges don't discharge. This process is called discharging. Maybe I'll drop that down. So this process is called charging the capacitor. This process is discharging the capacitor. So this process of discharging is not constant. The current don't flow really in a constant way, but at first, as soon as you disconnect the battery and reconnect it to a light bulb, all the positive charges are very happy there's a way to go to the other side. So there's a huge surge of charges to rush over the other side. And then there's less and less incentive because, as you can see, it will get closer and closer to equilibrium on both sides, so that there is 0 coulomb on this side and net zero coulomb on this side and net 0 coulomb on this side. Whereas here, there's a net positive Q and a net negative Q, right? So as they start flowing, you can kind of imagine they will get slower and slower because there's less and less incentive. When in the last straw, when there's only 0.1, there's only one positive charge left to go to the other side, that it doesn't have a very strong incentive to do that. It will move it very slowly. So if you actually connect this immediately to a light bulb, at first, the first 30 seconds, you'll get a very bright bulb, and then the next 1.5 minutes, it will slowly get dimmer and dimmer like that until it runs out. So it's not very constant. Nowadays, if you take a more sophisticated power bank, when you plug in your iPhone, or when you charge it with something like that, it might have a little bit of that exponential effect, but it's overall they make it pretty steady. So that is beyond the syllabus of our case on how do you make it a steady flow. So that's more of an engineering problem. So as a physicist, we'll delegate that to the trained engineers to sort that out. But we'll first learn the basic ideas here first. Now, you might have seen one of these things if you try to Google a capacitor, what it looks like. And this looks nothing like what I've just said of 2 metal plates. All right, what's going on here? Oops. Sorry, things just crashed. Oops. Okay, sorry. All right, so if you Google, you might see one of these little cylindrical things that if you try to Google what a capacitor is. So what is going on over here? Let me send you a slide. Is this, if I take 2 kitchen pans and put them next to each other and connect to a battery, in principle, yes, you can make a capacitor that way. By the way, the word capacitor probably comes from capacity, of the capacity of storing charges on it. Yeah, so call this, how do they make real capacitors? I'll put it in double quote because what I've described is a real capacitor. Well, we shouldn't discriminate against that capacitor. But when I say real, it's like in real life. So you see these little cylindrical things with 2 legs like this. So what they're really doing is, if you take 2 pans like this, it's not very economical, right? You don't see a huge pan when you try to charge your iPhone every time. So what they did is very clever. You take 1 sheet of metal, and first you wrap it up in a cylinder-like form like this. So I'm just drawing the top view. Okay, so from the top view. So you take the sheet of metal, instead of having a sheet like this, positive sheet of charges like this, you should wrap it around. And then now you take the second sheet, which let me denote it in blue, and you wrap it right next to the black one. So the black one is where you put all the positive charges, and then the blue one is where you put all the negative charges, right? So negative. So okay, I won't draw too much label, but imagine the blue one is full of negative charges and the black one is full of positive charges like that. And then I can connect this with a leg out here and then a leg out here, right? And then have this connect to one side of the battery, and then this is the positive side of the battery, like that. Okay. So this side is negative. Yeah, this is the negative terminal. This is the positive terminal with 9 volts with 0 volt like this. And now you can push all the positive charges on the black plate and push all the negative charges here. And it's a very compact thing. So you can see these 2 legs. This one side is positive. You connect it with a wire to positive and negative. Right? It's pretty clever already. But furthermore, there is a potential danger here is, imagine what happens if these 2 plates touch. right? Then you suddenly neutralize everything. Imagine if you touch, you create a short circuit, and all the positive charge now just flows back to the battery, and then negative charges flows back to the battery on the other terminal. So what you need is to prevent them from touching, especially when you have this tiny little device like this. It is impressive, truly impressive how they make it so small. This is real good engineering work, right? And not touch. Well, how do you make it not touch? So whoever came up with this idea is really clever. You basically just fill up the middle part with an insulating material, like plastic or glue. And you fill it up like this so they can never touch. In fact, you can fill up I should actually fill up every space because you need to prevent them from touching, right? So you fill up everything by usually they use some kind of glue, which not only serves the purpose of sticking it together so that it doesn't come loose, but also insulating. It's a perfect piece of engineering over there. This looks like a snail, but that's that. So write it out. So this is some insulating material. And engineers invent a name for it. It's called dielectric. Don't ask me why, but it's just a fancy word of insulator. It's an alternative word for now. I mean, as far as we are concerned, it's just a different word for insulator. Don't have to worry about too much of that. All right, so I've showed you a real little capacitor. Now let's think about so now we know what it is, right? We know what a capacitor is. So how do we measure it? And how do we make it better like that? So the next thing is, did I give you the proper definition? All right, let me give you the proper definition as well. Capacitor is a device that stores charge. In the simplest terms, that's what it is. So remember, a battery is a device that creates a potential difference, and a capacitor is a device that stores charge. Very simple. All right. The symbol, the circuit symbol, if you want to put one of these in your circuits, what is the symbol we used to draw? It's very simple. There's two plates like this, right? So be careful. The two plates here should be rough. It should be equal length. If I draw that properly. Right. So when you in the charging phase, you want to connect a battery to this. You can draw that nice and square if you want. Right? So it's a little bit confusing, but try to exaggerate the battery if you can to clearly distinguish what is a battery, and even better, you try to label this as epsilon, so we know without a doubt that's a battery. So that's the charging phase, and then the discharging phase is when you connect this to some resistor. It can be a light bulb or whatever. We can label it that way. Okay. So that's the circuit symbol. And then, so how do we quantify this? It's a device that stores charge, and the idea to quantify the quantity, the actual physics, remember what do we mean in physics by quantity, is something that's measurable, right? It's a variable that you can actually assign a number to. So it's called capacitance. We use the symbol C for it. Okay. C for capacitance. And so let me write it in layman first. In layman terms, in a layman definition or a simple definition is, it's a capacitance measures how powerful a capacitor is. This is not a technical definition, but if you want to explain it to your parents tonight, that you've learned what a capacitor is and what is capacitance, they don't need to know all the equations. You can tell them basically measure how powerful the capacitor is. Okay. So capacitance is the quantity. We'll assign a number to it. The SI units, as we'll see, the SI base unit is called farads. Must be a tribute to the scientist who was working on this. We use F like that. We assign a number like 5 farads, 5 millifarads or whatever, and that tells you what. So the capacitor is the device, capacitance is the measurement of it. Just like resistance and resistor, right? Resistance is measuring how much resistance the resistor has. So resistor is the device, and resistance is the measurement of how powerful that resistor is resisting. Okay. All right, so that's the layman definition. The more technical definition is, let me write it on the new page. So capacitance, the more technical or formal definition is the amount of charge it can store. But if you put it to a larger battery, if you take the 2 plates, you plug it into a larger battery, of course it can store more charge. So so it's not fair if you say I have a strong capacitor and a weak capacitor, but then the weak capacitor I connected to a battery that is 100 volts, and then this one I connected to a battery that is 1.5 volts, right? And then you say this guy stores more charge. That's not a fair comparison. You should compare them with same potential difference that you're putting across them, the same voltage that you're putting across them, right? So it's the amount of charge you can store per unit volt, right? Per unit potential difference. Okay, now it's a fair comparison, right? So everyone, let's plug it with 1 volt. Let's see which one wins. Let's see which one can store more charge. Now it's a good comparison. All right, so in the equation, if you like, then you can write it as the amount of charge you store per unit potential difference, like that. And if anyone have been following up with this reading, with the textbook reading as well, you'll see that every time in circuits, they start dropping all the deltas, even though they're talking about potential difference. I highly recommend any beginners, when you're starting out, don't do that. I still don't do that because it will make the previous chapter of what you've just spent the whole of week 3 trying to disentangle the difference between potential difference and absolute potential. Right? Don't make all that hard work go to waste. We are always talking about potential difference in circuits and not the absolute potential. So you might want, this is a very good idea. And also, as maybe the next thing I would say is, how do you label it in a problem solving context? This is the best way to label it, just like how you label a resistor. To label a capacitance, I would put a delta V across it like this, okay? And that's the best way to think about it, because potential difference or voltage is always across 2 points. Let's say this is has capacitance 1, so I can label it C1. So, if I have more than 1 capacitor, as we'll look at very shortly, like this. And on a resistor, just to mirror this, you can label each resistor R1 and label each of them the potential difference across them like this, right? Just like a resistor, the most dependent thing out of this is the current. So the current I1 that flows through it is dependent on what the potential difference across it is and what the resistance is. If you have a small resistance, then there'll be a lot of current. If there's a large resistance, then there'll be very small current flowing through it. Right? So here, the thing that is most dependent is how much charge you can put on it, right? The larger the potential difference you set up across its 2 sides, then the more charge you can store on it. So what you would want to label is plus Q on one side, negative Q on one side. Okay? The plus and minus depends on which side you're connecting to the battery. Okay? So I didn't draw the battery here, but in general, you have one side that's positive, one side that's negative. If you have more than that, if you have more than 1 capacitor, you might want to label that Q1 and minus Q1. Make this a little bit more pretty. Okay, so one side label positive Q1 and the other side label negative Q1. Okay. So here are the general ways how every time I do one of these circuit problems, it's my best way of labeling things. For battery, I'll just for completeness include that as well. That is the potential difference, is the EMF, assuming there's no internal resistance. So I'll change this into different colors because of how important I think this way of labeling things is. Let me actually make it red. So the point is, you want to label the delta VI across it, the capacitance, and plus and minus QI, okay, for capacitors every time. And for resistor, you will label its resistance, the current going through it, and the potential difference across it. Okay. All right. So here's a question for you. So we have, let me see. So I've got the technical definition in words. Right? So this is the definition in words, the definition in equation. I've got the SI units, which is farads. So this is how you can quantify it. Just make sure I have everything. Yep. Good. Okay, so here's a question for you. Let's make sure we understand this for this definition over here. When I have a capacitor like this, one side I will have positive Q, and the other side I will have negative Q amount of charge, right? So as we talked about, you will get charged up like this. So what does this Q mean? Right? Remember, when we label things, when we define things, we should define everything. So this is the potential difference across the capacitor. You can fill in the words. This is the capacitance of the capacitor. Right? Okay, so what does the Q mean? So these two are very simple, because I have 2 things over here. So do I plug in? So here's my question to you in pink. Which Q does the Q means in this Q? Sorry, there's a lot of Q. This is a question. So does the Q? Maybe I should. All right, I'll write this out. So the question is, Does the Q in C equals to Q over delta V, is the Q in here refer to A, the charge on, I was about to write Q on, but there's too much Q's. The charge on the positive plate, B, the charge on the negative plate, or, so put that in the chat, what do you think this is? Or the total charge on both plates. So which one of these, A, B, or C, should you plug into the formula to the formula or for the definition? Total charge on both plates. So, any guesses? C. Good. So I would think that as well. So this is a very, again, sorry for all the trick questions, but it's good to first think about intuitively what do we think, and then learn the right way. So you'll have a bigger impact, and you won't make the same mistake again. So we'll get that out of the way, out of our systems, right? Get the wrong intuition out of the system. So that's kind of what these little pop questions are for. Yeah. So let's see what the problem is. It sounds like this is actually a very common mistake students make. Is they'll think that it's, oh, you're just plugging the total charges on both plates. But what is the total charge? If you look at this for another 10 seconds, you'll realize that the total charge would be 0. No matter how much charge, let's say you store 100 coulombs over here and negative 100 coulombs, no matter how big your capacitance is, if you plug in the total charge here, then C would always be 0. That's a stupid way to define capacitance, right? Capacitance is supposed to measure how powerful, right? In layman terms, how powerful your capacitor is. So if you plug in the total charge, every time you'll get 0 because of that. So it's not that. And Anath has a great answer. Basically, yeah, you plug in the charge on one side. You plug in the magnitude of the amount of charge on one side. Okay, so you can think of it in two ways. You can think of, you plug in the amount of charge on the positive plate, or you think of the magnitude, or the absolute value or the magnitude of charges that get stored on one side, not on two sides. Okay, and a different mistake is, because if you realize that if you plug this in, it's 0, you probably won't do that. But some easy mistakes for beginners when they work with capacitance is they think I should plug in the magnitude of both, and then they plug in, if one side, let's say I store 100 coulombs. Remember, a coulomb is actually a lot, so these are huge numbers. That is not realistic, but just for illustration purpose, right? So some of them would think, okay, so there's 100 charges here, there's 100 charges, let me just put in 200. Again, you're double counting. That's not, well, you could make a definition that way, but that's not how it's defined. Right? In the community, we agree that it's just the magnitude of one side. So I'm not going to write that out, but maybe you want to give yourself a note over here. What does the Q mean? It's the magnitude of the charges on one of the plate. All right, so we still haven't talked about how do I make a good one, right? Now I told you how do I measure it. My goal is to put as much charge here as possible per unit potential difference, per unit volts. But what can I do, right? So let's think of it. Any guesses? How can I make a matter of two plates? What can I change about the plate to store more charge on it? While I write this out, you can pop some ideas and check how to maximize capacitance. Okay, or AKA how to make a better capacitor. Okay. Increase the surface area of the plate. Brilliant, exactly. Yeah. So let's look at the math if it agrees to this. This time it's not a trick question. So let's look at a parallel plate. So these are called parallel plate capacitors. So we have the positive charge, negative charge side. They should balance, right? So let's say I separate them with a given distance d. One side I'll get positive q, and I go negative q, and I have delta v over here. All right, so C is identical to this. Now the delta v is governed basically from the battery, right? And this, so this is the most dependent on, right? So this is the most dependent quantity. So it should depend on this somehow. So the question is how. All right, so first of all, let's look at the microscopic details over here. So you in the last week's short answer questions test, you might already see that the word capacitor popped up because I want to sort of introduce you to the word. It's basically the two parallel plates, and it will set up an electric field in the middle like this, right? So those are the field lines, and now you know how to calculate those. The electric field strength of one field line is sigma over 2 epsilon naught, but there's 2 that adds up in the middle. So now you should know how to do the calculation, they should be sigma over epsilon, right? Or Q over epsilon A, if this is a finite plate, like what we're using over here. So first, remember how does E relate to delta V, all right? So delta V is E times delta X, right? How much distance it changes. So if you forgot, here's a quick review. So delta V, the definition is you move from A to B. It's the work done per unit charge, so it's force times distance per unit charge, Q test. But this part is the electric field, right? So you can always write it like this, first of all. Now, the electric field is purely in the X direction, so let's just write it like this. Right? It has X, Y, Z components, but the other components, you can think of it as just 0. And what is dr? Dr is, it's a little change in distance. So if you have 3 dimensions, it's a little bit change in little movement in X, little movement in Y, little movement in Z. You do the dot product of this. So you have AB, and when you plug this in, so EX00 dot dx dy dz, you basically just get EX dx, right? Plus 0, these don't matter. After you do the dot product, and EX is the magnitude of, right, that it only has one component, so you see the magnitude is basically this, the total E field in between the plates. So if it's a constant, as you can see, it does not depend on X at all, right? It doesn't depend on how far away you are from the plate, as long as they're pretty close together and we are ignoring a little bit of edge effects, you can pull that out. Okay, so you do the integral, I'll skip right ahead to the end. You basically get this scenario. So delta V is the magnitude of E. In this case, it's just purely in the X direction times dx. Right, so let's call that D, and let's call this Q over epsilon A, right? So that's the potential difference expressed in terms of the area and the distance away from it. So what is the capacitance? Because we want to find out what affects this, right? What affects C? So C is Q divided by delta V, right? Which is Q D over epsilon A, right? So you plug that in there, and you simplify that, flip that on its head. You can check this carefully. So this is the result. So here we get a very clear answer that, so the answer is how to make a better capacitance. You increase or you maximize the area and you minimize D. Okay. All right, so you're right, intuitive. So of course, if you have a bigger plate, right, larger area, of course you store more charges. What is probably less intuitive without doing the math, you probably will not be able to think about it out of the blue, is that you also want to minimize the distance. So this is interesting, right? So this is something you probably won't learn without doing these 3 steps, that you realize the capacitance is inversely proportional to distance. So the closer you can get them together, the better. So that's why you see these guys try to make it, here's a nice little diagram, as close together as possible. Right, so that now you've learned something new. You've learned that this is the reason why they try to tug it and roll it up like a piece of dessert in a very, very close, tightly wounded way. Right? So they try to make the insulator as thin as possible, and it's quite an impressive feature. So here's some few more in different shapes, but they're basically the same idea. Look how small they can make. It's the size of probably your fingernails or pinky nails. And probably some smaller as well. It's very precise piece of machinery that makes these. All right. So one more piece of theory is, now that we know how much charge, but actually what we are interested in physics is really more about the energy, how much energy we can store on it, right? Because if I tell you on my iPhone, this capacitor stores 50 coulombs or 50 megacoulombs of charge, you don't really care. What you really want to know is how much energy is stored there. So how much power it can generate, right? Power is how much energy per unit time, the rate of change of energy, or how much power it can produce. So what we really want to know is how much energy is stored. Okay? So that's the best thing. So AKA is to find the delta U, right? So this is how much electrical energy or electric potential energy is stored in the capacitor. Right? So how do we think about this? So we know the formula of if I put one charge here and another charge here, so if I just have 2 charges, we know, okay, that's how much energy that is stored, right? Q1, Q2 over R. R is sort of the distance. So let me use D over here. So that's the energy. But now if I have millions of charges on both sides, how do I do that? Well, first of all, this is Q1 times the V, the potential created by 2. Let's call this 1 and 2. So I can think of Q2 as KQ2 over D. So this is, I can think of this as a source and this is a test, or the other way around, it doesn't matter, it's very symmetrical. So you can think of this guy as creating a potential, and this, you're trying to bring Q1 up to this potential, right? Up to this location, and it takes this much energy to do that. But now you need to bring a lot of things to this side, and also not only bring a lot of positive charge to this side against this, you also need to bring a lot of negative charge on this side against all these. So the total stored energy that is needed to put in there is you sum up all the little bits of energy. So remember how we read these in physics is a big change. So initially, initially this is not charged. So I'm going from initial to final. Sorry, this is the wrong way around. It's going from bottom to top, but from not charged to charged, from initial to final, I'm building these up little by little. So I'm analyzing how much energy do I need to build up each little charges. So from initial to final, okay. And each time I bring up a charge, I need to overcome, right? So remember delta U, I need to overcome that much potential difference. And that's the amount of potential energy, EPE, that is required to overcome that amount of potential difference every time I bring up a small test charge to across a certain potential difference. So in the test number, topic test 3, you have calculated moving between potential difference. This is how you find the energy that's required, right? So now let's rewrite this, right? So I can, let's see, C, so C is the capacitance is Q over delta V. So each time when I bring up a little bit, when it's just, let's say I just have one little charge over here, Q. So the temporary capacitance is that Q over that little bit of potential difference, which is not fully set up yet. So I can write it like this as a small Q and a, let's say a small Q and a small potential difference, or I can rewrite this way. So the amount of charge is C times delta V. But if I just want to bring up a small charge against it, so that is the relationship there. Okay, so I can rewrite this as Q dV is dQ over C. So C depends on the, what does C depend on? C depend on, what do we find? We found the area and the distance, right? So it's pretty much a constant. As long as you have a given area and a given distance across it, then C is a constant. You can pull that out. Initial to final, Q dQ. Okay, so here's an integral that most of you can do. It's just 1/2 Q squared, right? And we need to go from initial to final. So initially, it is when the charge is 0, and at the end, you want to charge it up to a full amount of capital Q. So you put that in and you will get Q squared over C. Okay, so this is the formula for, let me put it in a box. So this is a derivation where you can just refer to where it comes from once in your life. You don't need to know this for exam, but you need to know the final result is this. Right? So Q is the total amount of charge that is stored on the plate. C is the capacitance, and this is the amount of energy in joules that you have stored inside your capacitor. Right? So this is a useful information because now that you know if I tell you the capacitance, in principle, you can calculate how much joules it stored, and then now you can connect this to, if you have a huge capacitor. In fact, this is used to jumpstart cars, your car engine. If your car stalls and in the middle of the road and you need to jumpstart it, what you can use is it's basically a battery to quickly discharge it, and the battery is basically that is a battery that stored that amount of charge and to jumpstart it. So you need to calculate how much energy, how much joules of energy you can provide like that. Okay, there are a couple of versions precisely because of this that you can rewrite things. There are several ways you can rewrite things, right? You can rewrite it this way. You can, just like after you learn that density is mass per unit volume, you can always rearrange these things to make it convenient in whatever problem you need to solve. So you can rewrite it in different ways. So if you plug in C equals to Q over delta V, right? So you can replug this in and you can get this, if I've done it correctly, or you can just eliminate one and you can get, Q times delta V. Let's see, so if I plug in C over here, so I have Q delta V. Yeah, so I probably would get this one more directly first. and then other. But yeah, so you can rearrange it in either way. You know, sometimes the problem don't give you C or doesn't give you Q, then you might want one of the other versions. It's like this. Personally, I won't remember all of them. I remember the first one because that one comes directly out from first principles, from derivation. And then if I need it, I'll rearrange it. In practice, probably this is actually the most practical one. Not saying in problem solving, because, you know, in problem solving, sometimes you conjure up with some very contrived examples to do. They'll give you two of the variables and ask you to solve the third one. But in real life, what you really usually know is, you know, the capacitance of the object. If not, just look at the area and the distance, then you know the capacitance. And then you know how much potential difference. You take a voltmeter, put it on two ends, you measure the, or just look at the battery or what you're connecting it to or whatever. So these are usually what you can measure. It's harder to measure the actual Q, the actual charge, right? How do you go and actually count how much electrons is on each side? That's harder to do. So in practice, that is more. So in everyday life, that is more useful. All right. Yeah, okay. So the last thing is we'll try to integrate this in the circuit and look at them in, we have the formula for if I put two capacitors in parallel and in series, what do they do? Do they add up? If I want to store a lot of charge, should I, and I have a couple of power banks, should I put them in series? Is that the best use of my time, or should I put them in parallel? Is that the best way to do? So let's see what happens when you put capacitors in series. Series and parallel. Okay, let's start with parallel. It's a little bit easier. Okay, so in parallel, I'll tell you the answer first. And this is slightly, you need to be slightly careful because the formula for series and parallel for capacitor is actually exactly opposite to those of resistors. Okay, so just to remind you, for resistance, to find the resistance of two things in series, you add them. Right? In series. In parallel, you add the reciprocals, and that will give you the reciprocal of the equivalent capacitance. Okay? But for resistance, for capacitance is exactly the opposite. Okay, so I'll give you the answer right away. In series, if you put them in series, this is what happens. This is the right way, and in parallel, it's the other way. So it's just adding them up. Okay. And it's actually pretty easy to know why. It's just, you have to be careful. So if you want to start constructing your cheat sheet for the final exam, or formula sheet for the final exam, that you probably, these two boxes is what you want to put in there as well. And remember to label which one's series, which one is parallel. I would definitely include that there. You don't want to, because you don't want to rederive them every time. But the answer, the derivation is pretty simple. Is this? So think about, if I have a capacitor like this, okay, and I will want to take a piece. First of all, I will split my wires like this to connect them, to connect the two plates like this. Okay, so I haven't changed anything, right? So this is C, this is plus Q, this is minus Q. There's a certain potential difference given across them like this. All right, so all is good here. So nothing really changed over here so far. All right, so it's the same thing, right? There's plus Q, minus Q, right, like that. Now I take a pair of scissors and cut in the middle like this. Okay, so now I've suddenly made two capacitors out of one capacitor. So let me redraw this, and it will look exactly like a parallel configuration, right? So I can call this Q1 minus Q1. And Q2 minus Q2 like this, right? So this is capacitor number 1 and capacitor number 2. I've made two capacitors in parallel out of just basically just chopping the first one. Okay, it's good enough. All right. So what do we learn from here? Okay, so what we learned is, now let me relabel everything. I'll relabel delta Q here. I'll relabel a delta V1 here like this. All right, so what do we learn? First of all, if you stare at this side, this plus this should definitely just equals to whatever we started off with, right? So let's call this the equivalent capacitance, right? So equivalent, that's what the equivalent potential difference. So looking at a blue plate, we see that Q1 plus Q2 should add up to the equivalent amount of charge, right? Because I just basically cut it straight through, right? And this is the same amount of charge, and I've split the wire. that doesn't change anything, right? So imagine I just split up the wire. It shouldn't change anything when I'm connected to battery. If it can store 100 coulombs on here originally, then just by splitting the wire, it wouldn't change the amount of charge. Just cutting it across wouldn't change the amount of charge. I've really done nothing important over there. And on the orange side, what is the equation we can set up? We can set up minus QEQ equals to minus Q1 plus minus Q2, right? So I can cancel out the minus signs, which basically give me the same equation, right? So that's a redundant information, but it's good to check. There's nothing new. So maybe let me erase this. It's not that important, but you can actually compare and double check that everything is good. What else is related? Let's look at the potential difference, right? So just by splitting the wire in that triangle that we did, or in this bracket, doesn't change the potential difference, right? This point is the same as this point. This point is still the same as this point in terms of potential. So we deduce that not only V1 equals to V2, but this is all the same as VEQ. All right, so I will put a box around this, but this is not something you would want to memorize off your heart, because if you do, there's too much things in life to memorize. But what we're going to get out of this, but you need to know how to deduce this, because in this alone will not serve all of you well with all of your problems. You need to be able to infer these relationships. I just wouldn't memorize it because next we will look at a series case, and then it's completely opposite. You know, so learn how to draw this diagram, learn this logic. Earlier I say this derivation, you probably don't need to know it by heart. I wouldn't memorize this, but this logic you should, because it's about helping you with problem solving later on. Okay. Right, so what do we go from here? And then it's good to keep this in mind, the definition of capacitance. Right, so let's plug this in here and in here and see what we learn. So if we plug it in the potential equation, we get QEQ over CEQ equals to Q1 over C1 equals to Q2 over C2. All right, so good. So what this will help you is if, let's say if you know CEQ and you know C1, or let's say if you know C1 and C2, and if you know Q2, you can find Q1, right? So for problem solving wise, don't try to memorize every single of these relationships. Just know these three facts, the definition, plus know how to derive this out of your labeling, and then you can deduce all these things in your homework problem, right? We'll give you, for example, give you C1, C2, and tell you what Q1 is, and then ask you what Q2 is, and then this is how you can find it. And what can we learn out of this is CEQ delta VEQ, right? Use plug in the definition is C1 delta V1 plus C2 delta V2. Okay. All right. In fact, this can be simplified because actually all of these are the same. So I can actually divide them out on both sides, and I got this equation. Okay, so I will put a box around this. This one, I'll put not only a box, but I'll put a star as well, because this is one that I will actually remember. So this is where that comes from. Okay. But learn the logic here is what I recommend, and learn, because this would be equivalently useful, but I just wouldn't put this as a formula per se. All right, so that is in parallel. So you see where that comes from. So I'll finish off with the series as well. This is probably the last main thing. Yep. All right, so in series, let's again start with, imagine a big capacitor like this. Okay, I'm going to copy this and put it here. And this time, right, so plus Q minus Q, right, C with some delta V across it. Okay, I am going to insert a piece of metal here, like an H diagram over here. So it's just another two pieces of metal connected with a wire. It's a big piece of conductor. All right, what's going to happen? So originally I have plus Q over here, right? But you see now I've suddenly made two capacitance out of one, right? I made two capacitors in series like this. Now, if I now relabel this as Q1 minus Q1, so as this is capacitor 1, capacitor 2, and positive Q2 minus Q2, right, on this side, like this, and write, this is going to be difficult to squeeze in, but we'll try our best, right? Delta V1, delta V2, like this. I'll put that on top, maybe that's a little bit easier. Delta V1 and delta V2. Okay, so what can we learn out of this? First of all, putting a piece of metal here doesn't really change the charge on here. So it's just like me slapping a piece of extra metal over here. It shouldn't change the Q. So Q over here should equals to Q1, right? Whatever's on this black plate over here is exactly the same over here. And whatever's on this orange plate on this side should exactly be here, right? So the first thing I learned is Q is equals to Q1. And on the other side, the orange side, I learned that minus Q is equals to minus Q2, okay? Which means Q is equals to Q2. How about in the middle, in the blue part? If I stare at the blue part over here, this side I have minus Q1 of charge, but this is a neutral piece of metal, right? Remember, I just put a conductor there. And if there is minus Q1 on one side, the other side should be positive Q1. So if this side is minus Q1, this side should be positive Q1, right? So Q1 has to equals to Q2. So that's another thing I learned, right? There's many ways to think about it. You can think about it the way I just said, or you can think about a conservation of charges where minus Q1, if you look at the blue part, minus Q1 plus Q2, right, equals to 0 because it's neutral, right? This starts off neutral. The net is neutral, I should say, right? Just put a neutral piece of wire and then the charges separate. So now you infer that Q1 equals to Q2, right? And of course that is true as well. If you combine all of these together, let's just put in one big box. That what do we learn? We learn Q is equals to, let's call that equivalence because that's what I'm going to want to derive, right? So Q equivalent is Q equals to Q1 equals to Q2. Okay. Does that make sense? Right. So hopefully that matches up, right? The blue part tells you Q1 equals to Q2. The black part tells you Q equivalent equals to Q1. The orange part tells you negative Q equivalent equals to negative Q2. And they all put together. Now let's look at the delta V's. So delta V1 plus delta V2 must be the big delta equivalent. So that's another thing we learn from just looking at this. So learn how to deduce these relationship out of your labeling. So learn how to label it and learn how to deduce these equations out of this. Okay. So finally, I want to see how the capacitors relate. Let's do our trusty trick of use the definition of capacitance and rearrange things and plug them into both of these box equations. What do I learn here? I learned that this is CEQ delta VEQ equals to C1 delta V1 equals to C2 delta V2. So some problems may give you the two capacitance and then give you one of the potential difference and ask you what's the other one. You can find it out this way. Or if you know the overall equivalent potential difference, and so you know this, and then you know, let's say you got this and you got C1, then you can deduce what V1 is. Or you can, if you know C2, you can deduce what V2 is. So a lot of the homework problems are something similar to this kind of situation, right? So we'll give you all this the capacitance, and then you know the overall potential difference across it. Maybe this is slightly better. So we'll tell you, okay, C1, what are the capacitance of each guy, and then there's an overall potential difference across it. So you can, so sometimes it's not as simple just as a series or parallel. Sometimes you have both together, right? You have two in series, and then these two are in parallel with the first one. So if you can draw these diagrams, then you will be able to solve these problems, right? Just as an example, the potential difference across C1, you see, is the same as V, right? And the potential difference across C2 and C3 will add up to V, right? So just knowing how to put in these little brackets and and labeling. And for example, the Q2 and Q3 over here, right, should be the same because whatever charge is on this side has to be on this side because of this part is neutral, right? The wire starts off neutral. Okay. Can you guys see this? Yeah. So so these are the type of problems you'll encounter, but let me finish off by plugging this in here. What do I get? I need to plug in delta V, so let me rearrange. Delta V is Q over C, all right, good. So we have QEQ over CEQ, and Q1 over C1, Q2 over C2. All right, and then we also see that all the Q's are the same, right? So they can actually cancel. And I got basically my equation that I alluded to. And so this one in blue, I will probably memorize in series. This is CEQ in series. And this is CEQ in parallel. All right, good. So this is the end of it. And like I said, the homework is up. Yeah, all right, yeah, so I think I'm improving just a little bit at a time in terms of my pacing. So this is the end of it. And let me make, if you can stay for 5 more minutes, I'll just explain some admin about the next topic test and also about some ways you can improve. And I'll try to keep it within 5 minutes. Okay, so the next topic test actually will not include tomorrow's lecture. So tomorrow we'll start magnetism. So this is all about circuits, right? In tomorrow's discussion session, you'll, one session, so there's 3, one of you will deal with capacitors. So you might get one of these problems that I just showed you here. So something like this, right? Or something like this. And one discussion session will look at Kirchhoff's rules. One other one will look at just circuits without Kirchhoff rule with power and currents and circuit resistance like that. Right? So these are the 3 main lectures from Monday to today. Monday, Tuesday, and Wednesday lecture 14, 13, 14, and 15. These will be included in the topic test. And tomorrow we'll start the magnetic force. So show you the course just to illustrate the point. Oh, I have not updated this. I thought I did. Okay, I will. Yeah, so the next topic test, test 4. Yeah, so it will only include these 3 lectures. And then the next one, lecture 16, will be tomorrow. Well, after your discussion session, we'll start on magnetic force, and it should last us all the way to lecture 18. Okay, and that, if everything goes well, that will be the end. And I think we'll use one lesson to do review and maybe some problem solving. And then one also fill in some of the more advanced topics, which is actually not covered normally in a 3B class, so you get your money worth. Then you're not learning less than the normal quarter, and it's also part of my obligation. I do have to, in some sense, you know, not completely skip over everything and give you those kind of topics. But I think personally, I think for a summer session with this rush, I don't want to, I think it's just too much stress to test everything in the normal quarter. So I won't, those are probably more challenging ones. I won't include it in even the final exam, but hope you understand that those are the 2 reasons why I will cover it. And some of you are doing an MCAT exam, so it will be there. Hopefully you've learned the skills, how to learn those things on your own. But I'll also sort of give you some initial steps and guidance. Even if you're not taking an MCAT exam, they're pretty interesting topics, and we'll do that. All right, so question here, a private question. So lecture 13, 14, 15 are the only ones for homework 4. Yes, that's right, yeah. Magnetism I won't make that in that will go into homework 5, as you can see. Okay, finally, one quick advice is about doing well. So how to do better in the course. I think now we're more than halfway in the course. So just a personal piece of advice is if you are happy with the grades you're getting so far, whether it's from the topic test, even if you don't get the grade back, you look at grading key, you can grade it yourself, right? So if you're happy with everything you're doing, just keep doing it, right? So this piece of advice doesn't apply to you. But if you're struggling and you'll see that you're struggling with every topic test, maybe consider doing something different. Very simple logic, right? If you're happy with it, keep doing it. If you're not happy with it, if you keep doing what you're doing right now, this is the tough love kind of part of this. Hate to break it to you, if you keep doing it, you won't get better. So what should you change? Ask yourself, are you going to discussion session? Because they are teaching different skills from the lecture. In some sense, my lectures actually help you with short answer questions. Okay, and the discussion session help you with open response questions. I know I might be addressing the wrong audience here, because if you're showing up to live lectures, you probably are diligent. You are probably one of the diligent students who go to every discussion session. But hopefully, watching this in recording, so take some value and advice out of this as well. And just to clarify, the short answer questions are not in principle, it's not enough you just attend the lecture, because in the lecture, since the very first lecture, I was mentioning to you that within a short amount of time, I'm telling you all the key bits from the textbook you need to learn. So the main responsibility is on your end to read up on these topics that I handpick. So I'll tell you which ones we want to focus more on and which ones are advanced topics that technically it's in the syllabus, technically you should learn about it, but we just due to the limited time and everything, we won't cover that in the final exam. So if you don't rewatch the lectures or you don't attend or don't rewatch the lectures, you might have the danger of learning something you don't need to know. So we won't want that, right? So this is what the lecture is for, is to tell you what you need to know. And in the textbook, you want to relearn that. Now there's a caveat is if the textbook is not doing anything for you, then feel free to use any resources you like. We're all adults here, and this is what we want to train you to do as well. Personally, in my college year, this is how how we learn as well. Use any resources you like. Personally, when I study all this, YouTube is a great resource. Look at how people solve problems. There are plenty of great graphic designers who make brilliant videos. Highly encourage them. If you find anything useful, feel free to share it on Piazza and benefit everyone. So that's so both reading the textbook and the lectures will help you with short answer questions. The homework and the discussion sessions will help you with the open response questions. All right, so this is my tip on what's going to happen. So if you're already doing all 4 of these ingredients, if you're going to lectures, reading the textbook or other resources, going to discussion session, homework, you should be doing well, right? If you're not doing any of these components, including reading a textbook, highly encourage you to start doing that. I think that's the best way to change. All right. Okay, so that's all I have to say. Hopefully this is helpful in just general advice as well as physics advice. Okay, good. All right, thank you for sticking around. Have a good night, and we'll start magnetism, final topic tomorrow. Have a good night.